In this video, we're going to talk about different number bases. Binary numbers are said to be base 2. We'll also talk about base 16 numbers, which are called hexadecimal numbers. Decimal numbers are base 10. We'll talk about how to convert back and forth between decimal and binary, and between decimal and binary and hexadecimal. Before we get started, I want to remind you how exponentiation works and point out a few numbers that it's important for you to memorize. Remember that when we raise something to a power, like 2 raised to the third power, it means to multiply that thing by itself, in this case 3 times. So here's 2 to the third power. It's 2 times 2 times 2, 3 times, which is 8. Likewise, 2 to the second power is 2 times 2, which is 4. And 2 to the first power is 2. Anything to the first power is that thing. So for example, 37 to the first power is 37. And anything to the 0th power is 1. So 2 to the 0 power is 1. Likewise, 37 to the 0 power would also be 1. So these numbers, of course, you know, but these are some additional numbers that you should commit to memory. Every computer scientist should know these numbers by heart, and every good computer scientist does. 2 to the 4th is 16. 2 to the 5th, 32. 2 to the 6th is 64. 2 to the 7th is 128, and 2 to the 8th is 256. You can probably recreate these numbers if you need to, but it's probably better just to go ahead and memorize them. You can memorize this sequence: 1, 2, 4, 8, 16, 32, 64, 128, and 256. Notice that each is a doubling of the previous one. So 8 is just 2 times 4, 32 is just 2 times 16, and if you double 32 you get 64, doubling it is 128, and doubling that is 256. Remember that with 8 bits of information, we could store 256 possible combinations. 2 to the 8th is 256. This is also true of decimal numbers, and you should, I'm sure you know that 2 squared is 100, and 2 cubed is 1,000, and 2 to the 4th is 10,000. With decimal exponentiation, you can see that the exponent tells you the number of zeros. So if you have a large exponent, remember you can just count the zeros. So here we have 1, 2, 3, 4, and that's 10 to the 4th. And of course, anything to the first power is just that same thing, and anything to the 0 power is just 1. Of course, we say anything to the second power, we call that squared, and anything to the third power, we oftentimes say that's cubed. So this is 10 cubed, and this is 2 cubed. Here are some other numbers that I'd like you to commit to memory. 2 to the 10th, 2 to the 20th, the 30th, and 2 to the 32, or 2 to the 32nd power. 2 to the 10th is more familiarly known as 1K. That number is 1024, and you should memorize that number. And notice it's about 1,000, not quite exactly 1,000. In many other domains, K means 1,000. For example, a kilogram is we use the symbol K for that as well, and in the case of grams, K means exactly 1,000. But when we're talking about binary numbers and computer memory, K means something slightly different. And this is a point of confusion, so it's important to understand that when we're talking about memory capacities of computers, K, M, and G do not mean exactly 1,000, 1 million, or 1 billion, but they mean something that's close to that. So 1K is 1024. 1 megabyte is about 1,000,000 bytes. It's actually a little bit more than 1,000,000 bytes. 1 gigabyte is about 1 billion bytes, but it's actually a little bit more than 1 billion. And 2 to the 32nd power is 4 gigabytes, or 4 gig, and that is approximately 4 billion. but as we saw before, it's a little bit more. The accuracy, or the difference between 1024 and 1000 is only about 2%, a little over 2%. As we get larger here, the relative difference is even greater. And so any comparison between decimal numbers like a million or billion, trillion starts to get tenuous. But these will give you an idea of the general order of magnitude of a number like 2 to the 30th. Now let's go back to number representation in decimal. This is stuff that you learned in grade school. Here's a number, 4,037. Remember that this is really composed of 4 thousands, 0 hundreds, 3 tens, and 7 ones. So here we can spell this number out as follows. We have 4,000, so 4 times 1,000. We have no 100s. We have 3 tens, and we have 7 ones. Now, we don't have any digits greater than the thousands place, so no 10,000s or 100,000s or millions. Sometimes we write zeros in front, but the zeros in front are not significant. So I've suggested with my ... here that this pattern continues to the left infinitely, but they're all multiplied by 0. So you only need to consider the 4, this 0, this 3, and that 7. Now let's look at these multiplying numbers, the place values, using exponential notation. 1 is 10 to the 0. 10 is 10 to the first power. 100 is 10 squared. 1,000 is 10 cubed. And 10,000 is 10 to the fourth, and so on. So we see that what we're doing is we're taking these individual digits, not 4,000 but just a 4, not 3 tens but just a 3, and we're multiplying them by some power of 10 depending on where they're located. The 3 is located here, so we're multiplying it by 10 to the first. If the 3 were located someplace else, we'd be multiplying it by a different power of 10. So in general, when we have a base 10 number, we perform this kind of computation to find out what value it really is. So these are decimal numbers, and that's why we use 10 as our base. In the decimal number system, we have exactly 10 digits, 0 through 9. And so in red, you see the actual digits. And then in black, you have information about what they mean or how to interpret them. And so the system is keyed on the position of the actual digits in the number. The reason that humans use the base 10 decimal number system is, of course, because humans have 10 fingers on their hands. On my home planet, we have 8 fingers on each hand for a total of 16 fingers, and so we count in the hexadecimal number representation. So it's a base 16 system. So let's take a look at how that works. Before I give you an example number, we'll have the digits represented here as x, but instead of multiplying them by 10 to some power, we'll multiply them by 16 to some power. So these factors here, 16 to the first, 16 to the second, 16 cubed, and so on, show the values of those places. 16 to the 0 is, of course, 1, and 16 to the first power is 16 itself. 16 squared happens to be exactly 2 to the 8th, which is 256. And it turns out that 16 cubed is 4,096, and 16 to the fourth is 65,536. You don't need to memorize these numbers, just to remember the general order of their size. humans in the decimal system use 10 different digits, 0 through 9. But in the hexadecimal number system, we need 16 different digits. So the digits we use are 0 through F. Rather than create some new symbols, we just reuse the first 6 letters. Now it's very easy to look at this symbol here, 5 for example, and think that it corresponds to 5. You can imagine 5 pennies or 5 apples or whatever. It's less easy to look at a symbol like this, D, and think that it corresponds to a number. But in fact, in this system it does. So you need to look at these symbols here and see that they're just like these symbols. This is 10. This corresponds to 10, so think of 10 apples. 11, 12, 13, 14, and 15. So these are not letters, but these are digits. We're just reusing the symbols from the alphabet in much the same way the Romans reused the symbols like I and V and X from their alphabet in order to make their number system. Okay, let's take an example number in the hexadecimal system. And the number we're going to look at is 3A0F. Now, I'm going to read hexadecimal number systems like that. If it were a decimal number, like in our previous slide, we had the number 4037, and we read that as 4037. We have a way of reading these things. There's not a similar way to read these. We don't say 3000 A 100. No, we don't say it like that. We just read it off 3A0F. In the same way we might read this number as 4037. So we're going to read our numbers in hexadecimal just by saying the digits in order. 4037 is a decimal number, and 3A0F is a hexadecimal number. So what number is it? Okay, it's some large number. You can tell it's large because it has several digits. But what number is it exactly? Well, let's look at each of the digits, and here I've listed them out. 3A0F, along with the multipliers, the 1s, the 16s, the 256s, and so on. Here I've shown the place values using exponential notation, and in the next line I've gone ahead and written out the actual values. So this number is 3 times 4096 plus A times 256. Wait a minute. A times, well, remember A is a digit, okay? And it means 10. So I might call this thing 10, so to say 10 times 256. And I might read this number as 310015, but that's not really the way people do it. They read it 3A0F, with the understanding that A means 10 and F means 15. So here I've translated the A to 10. We have 0, and then we have F, which means 15. So it's the number 15. So when you multiply this thing out, you get, what's this, 12,288. You multiply 10 by 256, you get 2,560. You have no 16s, and you have 15 ones. Okay, and then when you add it all together, you get 14,863, and that's expressed in our familiar decimal notation. So in this diagram, everything that's in red is in hex notation, and the other numbers are all in decimal notation. Here are the hex digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And here is their value. Of course, the first 10 of these have the same value as decimal, so that's easy enough to remember. But you should remember that A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So commit this information to memory. And the way I do it is I kind of remember that A is 10. That's easy enough to remember because it's the first one right after 9. And F is the last one. That's 15. And then you can work out the others if you need to. But I also sort of remember that C is 12. And then that gives me B easily and D easily. And E is just one less than F. So commit this to memory. In particular, A is 10, C is 12, and F is 15. We'll need that later. And being able to go back and forth between the hex representation of a number and the decimal representation of a number is very useful. Okay, let's try it with another example. I've repeated here the general formula for hexadecimal numbers. Numbers represented in base 16 are made of several hex digits, and each digit has is multiplied by its place value. And those place values are given by 16 to the 0, 16 to the first power, 16 to the second power, 16 to the third power, the fourth power, and so on. And here are the actual place values. So, and remember, we have a set of digits or numerals. Probably a better word is numerals. We talk about digits in the decimal system, so 0 through 9 are the digits. But each one of those is really a numeral, so it's probably more correct to say we have 16 numerals, and those are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Okay, let's look at a particular example. This time we've got the hex number 2CB. Now, since this hex number contains a C and a B, it's pretty obvious that it's in hex. And so we don't need to make any particular indication that this is a hex number, because it's clearly not a decimal number. But in other cases, when we don't happen to see any of these last 6 numerals in the number, it may be important to make it clear whether the number is expressed in decimal or hexadecimal. Okay, so let's go ahead and compute this number's value. And here we have the computation. So we can imagine that we have an infinite number of leading zeros that don't do anything. And then we have 2, C, and B. Well, here are the place values, 16, 16 squared, and so on. So we have 2 times 256 and C times 16. What's C again? Well, remember, it's 12. And B is just one less than that. B is 11. So we have 2 times 256. That's 512. And then we have 12 times 16, which is 192. And then 11 more. And adding those together, we find out that the hex number 2CB is equal to 715 in decimal. Now we understand how to express numbers in different bases. We know how to express a number in base 10, that's the familiar decimal number system, and we know how to express numbers in the base 16 system, and those are hexadecimal numbers. We can use the same idea to express numbers in binary. So here the base is 2. It's a very small number, much smaller than 10 or 16, so but it works just the same way. So each numeral in the number is going to be multiplied by a power of the base to show its place value. And instead of having 10 to the 0, 10 to the first, 10 squared, we've got 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, 2 to the fifth, and so on. So if you remember your powers of 2, the place values are 1, 2, 4, 8, 16, 32, and continuing 64, 128, 256, and 512, and so on, and then 1024. Instead of having 10 digits or numerals, or instead of having 16 numerals, which we have for the hex system, here we only have 2 numerals, 0 and 1. So let's look at an example binary number and see how we can convert it to decimal, see how we can figure out what its value is. So here's our example number, 110101. So let's do exactly what we did before. We'll write down our numerals, and here I can call them bits. Okay, we call the numerals in a decimal system digits, and we call the numerals in the binary system bits. So we have 110, 110, 101. And our powers of 2 are 1, 2, 4, 8, 16, and 32. So we multiply. We have 132. We have 116. We have no 8s. We have 1, 4. We have no 2s. And we have 1, 1. So adding these together, we get 32. Here's 20. So 52 plus 1 is 53. So this is the binary number representation for what we would express as 53 in the decimal number system. So here we're showing 3 different numbers, and we're showing one in the decimal system, one in the binary system, and one in the hex system. These numbers are different, they're not the same value. And we're showing above each number the value of the places. So here we have 48,293 in the decimal system. The place values are 1, 10, 100, 1,000, 10,000, and so on, continuing to the left. Here we have a number in binary, 101, 101, 110. And the place values always 1, they always start with 1. And then the base, 2. Here the base is 10, here the base is 16. And then in the case of the binary numbers, they just double, 4, 8, 16, 32, 64, 128, 256. And here we have a number in hex, and it would be read off as 4E, 7D, F20. And you can see that this number is quite a large number. It's got 4 times 16 million, so that's well over 64 million, plus 14 million here. So you can see it's a large number. But here are the place values for each individual numeral in the number. Numbers are represented in programs, and in the C programming language, we have this standard for representing hex numbers. This standard is also used in other programming languages, so if you don't know or care about the C programming language, you still might be interested in knowing how hex numbers are represented, because this is a universal standard that applies to many different languages. For hexadecimal numbers, we always start with a 0 and an X, and then we write the number. And in general, the numerals can be written either as uppercase or lowercase. So far, I've written them as uppercase, and I prefer to write them as uppercase, but you often see them expressed in lowercase as well. Decimal numbers are usually written without the comma in most programming languages, certainly for the programming language C. There's not really a standard for writing binary numbers. Sometimes we see a 0B prefixing a string of zeros and ones. But the thing that's most important to know is that when you see a 0x, the numerals following it are to be interpreted as a hexadecimal number. All right, now let's get some practice and try and convert some numbers back and forth between different bases. I've shown the place values for binary numbers and hex numbers because we'll need those in our computations. Let's start with this number. This is a binary number, 101101111, and we want to convert it to decimal notation. Sometimes you see a subscript to indicate the base of the number, and in this example we see a subscript of 2 to indicate that it's a binary number. I'm not trying to say 101 million, 101,000, I'm not trying to say 10 million, 110,000, 111. So I put a little 2 here to indicate that this is in fact a binary number. So let's just do it this way. Let's write 101 right under here. 101, 101, and then we end with 1, 1. So I'm trying to make these line up here. 1, 1. So we can see we've got 128 plus 32. Okay, that's 160. Plus 16, that's 176. And plus 4, that's 180. And 2 plus 1 is 3. So 183 is our answer. And that's what we see there. Okay, our next task is to convert this to base 10. To base 16. Now, I haven't really talked about it yet, but there's a very convenient way to convert numbers from binary to base 10. And our number is 1, 1, 0, 1, 1, 0, 0, 1. Okay? So what we can do is we can break it into groups of 4 bits each, like this. And then we convert the 4 bits individually. So this, if you recall, 1001 is really 8 plus 1, or 9. So this is the encoding for 9. And 1101, well, if you remember, I always remember 1100 is C, which is 12. Then this is D. So D9. And that's our answer. In hex, it's D9. This trick of converting between binary and hex works in both directions. So if, for example, you have a hex value, let's make it 8B, then we convert each one of those to 4 bits. 8 is 1000, and B, well, we know that C is, this is 1 less than C. That's the code for B, 1011. And so we can convert from hex to binary, or from binary to hex, quite easily. Now that's what we're being asked to do in the next example. We're asked to convert 2AE to binary. So let me write it like this. We need 4 bits there, 4 bits there, and 4 bits there. 2 is just 0010. A is 1010. And E is 1110. And so that's our answer. Let's 0010, 1010, 1110. And that's exactly what we have here. We can write a little subscript 2 to indicate that it's in binary. Now we're asked to convert a hex number to base 10, and the number is 13E. So let me go up here to our hex and write 13E. So we've got 1 times 256, that's easy, plus 3 times 16. Well, 3 times 16 is 48. So we add those together and we get 304. And then E is 14. So we add another 14. So we get 318. Okay? So 1 times 256, 3 times 16, plus 14. And I've written base 10 here to indicate that it's base 10, in case you might think that it was a hex number. Now we want to convert 150 to base 2. So let's go back up here. Our goal is to get 150. And let's think about what values we want for the different places. Let's start with the most significant. Is this number greater than 128? Yes, it is. The next value over here is 256, but 150 is smaller. So our leading bits are 0, but we have at least 128. So let's take 128 and subtract it from 150, and that gives us 22. Okay, so, and then is that greater than 64? Nope. Greater than 32? Nope. Greater than 16? Yes. So we'll subtract off 16 there. When we subtract this, we get, whoops, that's not correct, we get 6. Okay, so 22 minus 16 is 6. Is that greater than 8? Nope. Is it greater than 4? Yes. So we subtract off 4, and we get a 2. And 2 and no 1s. So our answer is 1001, 0110. By the way, in hex, that would be 9, 6. In base 16. So let's look down here. And we see 1001, 0110 in base 2. Okay. Our last task is to convert 301 to base 16. So we're going to do that the same way. 301. So is it greater than 4096 or any of these other numbers? No, so those are zeros. But 301 is greater than 256. So we subtract off 256, and we get 45. Okay, is that greater than 16? Yes. Okay, so we have some 16s in there. 2 16s is 32, 3 16s is 48, so we only can fit 2 in there. So we subtract off 32, and we get 13. Well, remember C is 12, so 13 is D. So our answer is D. Let me get rid of that stuff there. Okay, so our answer is 1, 2, D. And that's what we see down here. 1 256, 3 16s. Oops, that should be a, okay, that's a mistake. That should be 2. And 13. Okay. And so in the next video we're going to move on to talk about how binary numbers can be stored in memory and how we can break them apart into bytes and words.